So, transition metal alkyl complexes, and here's one to go on our title slide. Now, where does the chemistry of transition metal alkyl compounds begin? With W.J. Pope, and his 1909, beginning of the 20th century, report of the compound that has, again, the elemental analysis consistent with having one platinum, 3 methyl groups and an iodide. But again, here they didn't have the kind of methods that we have today to immediately conclude that this was the structure of this species. He knew he had methyl, he knew he had iodide, he knew he had platinum. He did not know in what method these, or in what fashion these things were put together. And indeed, at that time, and right up until the 1960s, people thought transition metal alkyl bonds were inherently unstable. There was no extensive chemistry of transition metal alkyl compounds right up to the 1960s because nobody tried. There was the prevailing wisdom that these species would be unstable, and so what was the point in bothering? But Pope had actually had one of these compounds right at the beginning of the century in the form of this one. And this is quite an interesting compound here because we can do an electron count on this species. This is going to be a platinum trimethyl iodide species. Platinum is in what group of the periodic table? Platinum is under nickel in group 10. Nickel, palladium, platinum. So it's in group 10. Each one of these alkyl ligands is a 3 electron donor. Now what we're going to have is one ordinary covalent bond. So one iodide acting as a 1 electron donor. The other 2 iodides must therefore be reacting as dative donors. So here we have an iodide triply bridging. So it has a normal covalent bond and it's acting as a dative donor to 2 centres. So if we count it for platinum, we're going to have a 14, 16, 18 electron species. So this is an 18 electron species through a triply bridging iodide ligand. Why would transition metal alkyl compounds be so difficult to get a handle on? Why was it that people were convinced that they couldn't be made? Well, if we look at the thermodynamics of these species in a similar way to we looked at the thermodynamics of group 13 versus group 14, if you look at the strength of isolated metal-carbon bonds, the interesting point, there are 2 things I'd like to bring. First of all, they're of the same order as main group metal-carbon bonds. So we look at these group 14 examples here. What you find in group 14 is the typical value is this one here for the silicon-carbon bond of 311 kilojoules per mole. It's a typical value for this group. What you do find in main group chemistry, of course, is that the strength of the element carbon bond decreases as you go down the group. The strength of this element carbon bond decreases dramatically as you go down the group, and if you consider why, it's because you get inferior orbital overlap, and so the strength of these bonds decreases. Remember, we discovered that alkyl lead compounds actually were thermally unstable with respect to homolytic bond cleavage to give radical species, because that bond becomes really quite weak because the large lead orbitals are not overlapping very efficiently with the smaller carbon orbitals. So by that stage, you're actually finding that the transition metal carbon bond strengths are better than those present in tetramethyl tin. Tetramethyl tin is not very nice to get on your skin, but it's a perfectly stable compound, not a million miles away from tetramethyl silane. So these bonds are comparable in strength. So it's not simply a thermodynamic explanation. It's just as favourable to basically take your group 14 elements and turn them into oxides and water than it is to take your transition metal alkyl compounds and turn those into oxides and water. But what you find is it's really very difficult to deal with transition metal alkyl compounds. So it's not thermodynamics. Well, we know if it isn't thermodynamics, then it must be the other one. It must be a kinetic explanation that we're looking for. So let's see if we can find a kinetic explanation. Couple of more detailed comparisons here. If you're looking for tetra-alkyl titanium compounds, you have to look very hard indeed. These things are very difficult to work with. Tetraethyl titanium almost certainly does not exist. Even if you keep that species at very, very low temperatures, you can't isolate it, you can't get any evidence for it. It almost certainly cannot be made. Contrast that with tetraethyl lead, which you can put into a car engine and will facilitate combustion under temperatures of over 100 degrees centigrade. So there's a huge difference between tetraethyl titanium and tetraethyl lead, despite the fact, if anything, the titanium carbon bond is stronger than the lead carbon bond. So it's not a thermodynamic, it's a kinetic difference. How does lead decompose? Well, we've seen that. Lead needs to decompose by a homolytic cleavage of the lead carbon bond, meaning we produce lead radicals and carbon radicals. That's the mechanism by which the lead alkyls decompose, homolytic cleavage. How then do titanium alkyl compounds decompose? Well, if you've got a titanium ethyl group, then there is a very, very important decomposition mechanism available for you. First thing we need to recognise is that tetraalkyl titaniums are not electronically saturated. What is the electron count for tetraethyl titanium? Titanium's in group 4, alkyl ligand is a 1 electron donor. You won't have a piece of paper for that. It's 8. So these species are very, very brilliant. Very, very electron deficient species. And that means they've got lots of vacant orbitals. These vacant orbitals are available to take up donors. What you find is if you have a titanium ethyl group, then what you will find is that the beta hydrogen, so this is the alpha carbon, this is the beta carbon, this is a beta hydrogen. The beta hydrogen will interact with vacant orbitals on the titanium center. And it will do more than just interact with them. It will actually eliminate into one of these vacant orbitals. So if you want to push curly arrows like a good organic chemist, then what we would do is we would push a curly arrow from this bond here to here, meaning there's a movement of 2 electrons with the hydride ligand to form a new titanium hydride species. And we take this pair of electrons here and move them to here to make an alkene. So what you get is a titanium alkyl hydride species and one equivalent of alkene. And that process is called beta-hydride elimination. But the decomposition does not stop there. Once you have a species which has a metal hydride, cis, so adjacent to a metal alkyl, then that's set up for another reaction that is called reductive elimination. And reductive elimination is just what it sounds like. What you get is clipping together of the hydride and the alkyl functionality, and that will give you a molecule of alkane, in this case ethane, and an unsaturated titanium species here. So this process is called reductive elimination. Why is it called reductive elimination? Well, clearly we're eliminating something. We're eliminating an alkane here. It's called reductive elimination because if, and we'll do this at the end of the lecture course, if you work out the oxidation state here is titanium 4, the oxidation state here is titanium 2. So there has been a reduction of the titanium from 4 to 2, and a species has been eliminated, hence we call it reductive elimination. Now, if that process is taking place, then what we get is we get formation of one equivalent of alkene and one equivalent of alkane. That is a signature pattern for this kind of reactivity. If you find by mass spectroscopy or whatever means is convenient to you that you discover that you are eliminating an alkene and an alkane, then that is entirely consistent with a reaction decomposition pathway that involves beta-hydride elimination followed by reductive elimination. So that can be spotted fairly quickly from the reaction products. How can we overcome this tendency to undergo reactions like beta-hydride elimination? Well, if you want to make stable transition metal alkyls, then you can apply one of two strategies, or probably both of these strategies in combination. First of all, you can block all the available coordination sites. So you saw that the way that that mechanism took place is that the beta hydrogen was coordinating to a vacant orbital on the transition metal center. If you sterically or electronically saturate your transition metal center, so there's no way the alkyl group can bite back and interact with that transition metal center, then you are going to prevent beta-hydride elimination taking place. How do you do that? Well, you add donor ligands. So we add ligands that will take up those vacant orbitals on the metal. Now here's a good one. DMPE. Does everyone know what DMPE is? Who here has encountered? Yeah, DPPE. What is DPPE? Oh, well, most of you by this stage should actually know the answer to that question. DPPE is, this is the E part. This is an ethyl or ethylidene bridge here. There's phosphorus and 2 phenyl groups on each end. So that is a bidentate diphosphine ligand with obviously a couple of lone pairs on here to donate to the same transition metal centre. And which transition metal centre have you seen it donating to? Nickel, of course. In topic 2, you make a DPPE compound. Now, what do you think the M stands for? If P stood for phenyl, what does the M stand for? Yes. So it is the compound which looks almost exactly the same, only this time we've got methyl groups instead of phenyl groups. Now, we're all experts on phosphine ligands now, aren't we? What effect will having substituted methyl groups for phenyl groups have on our ligand? It will make it a better donor, and someone at the front here said it will influence its steric properties. Yes, it'll make it less sterically demanding and more electron donating, which I guess is exactly what we want in the case of this titanium, which already has 4 ligands on it here. So you can make an octahedral compound here. Now, if you put one of these ligands onto a species that is an 8 electron species, how many electron species will you get? 12. So you will make a 12 electron species. So it's still not 18 electrons, it's closer to 18 electrons, but more importantly, it's now sterically saturated. You are wrapping it up. You know that you have a steric limitation of 6 ligands around the titanium centre, and you're getting to the position where that alkyl group cannot come back and bite the metal centre. Now, if you go to compounds of CO and cyclopentadienyl ligands from metals from about chromium to the right of the periodic table, metals that have already got a fair few electrons of their own, then you'll find there that all the transition metal alkyl compounds that you isolate are 18 electron compounds. So there are lots of examples of 18 electron compounds from taking the middle part of the group. So you either sterically saturate your species, or you basically go to 18 electrons, in which case the species is already electronically saturated. The other method we can have here, the other method is to use a special kind of alkyl ligand. So we have some examples of special kinds of alkyl ligand. This is a methyl ligand, this is a benzyl ligand, this is N-pentyl ligand here, this is a acetylide ligand, this is a trimethyl-silyl methyl ligand, this is a bis-trimethyl-silyl methyl ligand, and this is a tris-trimethyl-silyl ligand, and this is a 2,6 phenyl ligand. What do all of these alkyl groups have in common? Or rather, what don't they have in common? Exactly. None of those alkyl groups has a beta hydrogen. So if what you're trying to avoid is a decomposition mechanism that involves beta-hydride elimination, then a pretty good strategy to go about that must be to use an alkyl ligand that doesn't have any beta-hydrogens. And this makes a tremendous difference to the stability of these compounds, just avoiding the presence of a beta-hydrogen. One thing worth pointing out on here, we noticed that, or hopefully you noticed from that table, that the transition metal carbon bond strength actually increases as you go down the group. Now that was in contrast to the main group. In the main group metal carbon bond strength decreases as you go down the group. For transition metal triads, for example, titanium, zirconium, hafnium, vanadium, niobium, tantalum, the bond strength increases as you go down the group. So one way of making more stable metal alkyls is to go to higher second and third row transition metals. Another method is to work with ligands that have more S character. Now, what do we mean by that? We mean ligands where the carbon, the orbital available for bonding to the metal, has more S character. So in the case of an alkyl group, of course, an alkyl group has a carbon atom that is sp3 hybridized. So there is a quarter S character in that orbital that is bonding with a transition metal. If you move to a vinyl or aryl carbon, that's sp2 hybridized. So there is a third S character in the orbital that is bonding to the metal. If you bond it to an alkylide ligand here, or acetylide, which is somewhat easier to say, then you have 50% S character in your orbital. And so the greater the S character in the orbital bonding to the transition metal, the stronger the metal-alkyl bond will tend to be. And you can also increase the metal-alkyl bond strength by putting electron withdrawing groups on your alkyl ligand. So I do a lot of chemistry in my laboratory with metal C6F5 groups, so perfluorinated phenyl groups. And those make very stable, very strongly stable metal-alkyl compounds because of the electron withdrawing properties of the fluorine. How do we make transition metal-alkyl compounds? We can insert alkenes, obviously, doesn't say here, but in order to make a metal alkyl, then you need to insert an alkene into a metal hydride bond. Or we can do oxidative addition. So finally, the one that I should expect all of you to be able to answer, because I spent 3 lectures banging on about it, and that is the metathesis route. So if you had an alkyl lithium or a Grignard reagent, that is an organometallic of a more electropositive element, so you'd expect those species to react with transition metal salts, typically transition metal halides, to give you new transition metal organometallic species. So metathesis is a very general route, and we'll look at these a little bit later in the course. Titanium tetrachloride and 2 equivalents of this dialkyl magnesium, because of course we need to introduce 4 ligands here. 2 equivalents of this reagent, start at low temperature, warm it up to room temperature, and you produce a titanium tetraalkyl. This is a special kind of alkyl ligand here with these silyl groups. These are very bulky alkyl groups. By putting essentially more flab, more chicken fat, onto the alkyl group, we can hinder the alkyl group itself and use that, the actual alkyl group, as a partial umbrella on our metal center. Another example here, alkylation of tungsten. Tungsten is a 3rd row transition metal. You can actually fit 8 alkyl groups or small alkyl groups around tungsten. So this is an interesting example, tungsten octamethyl. Now clearly we have 2 lithium cations, so that species there is a dianion. So what's the electron count of octamethyl tungsten dianion? Which group in the periodic table is tungsten in? 6. So we have 6. This is going to be a 16 electron species. So even with just methyl groups, by the time we get to group 6, we're getting more respectable electron counts here. This is a very important compound, not least because I got my PhD working with compounds like this. But these compounds are very important in polymerization chemistry, in the chemistry of making things like polythenes. So what you have here is a metallocene dichloride, and we'll talk about those in the lecture on Friday. If you react that with an alkyl lithium, then you can alkylate the dichloride and produce these titanosine, zirconosine or hafnosine dialkyl compounds. But these are just examples of that same reaction we've seen so many times before. Metathesis between a metal chloride and a more electropositive organometallic reagent. Metal alkyls and the 18 electron rule. So the 18 electron rule was absolutely strictly obeyed when it came to carbonyl compounds. We've seen that it's really quite difficult to get to 18 electrons if you're using early transition metals and you're just using alkyl ligands. You're asking quite a lot of something that is a 1 electron donor on those occasions. There are examples of transition metal alkyl compounds which are 18 electron species. So where they are 18 electron species, we would expect them, and we find that they're pretty stable. So we've seen Pope's example here. We also have this one. This is a very classic example. This is iron bonded to 2 carbonyl ligands, 1 cyclopentadienyl ligand. So that is going to be a 17 electron fragment there, and another electron from our alkyl group. This is an 18 electron species, achieving an 18 electron count by having these relatively generous 5 electron and 2 electron donors in here. So those are 18 electron compounds which obey the 18 electron rule and have the stability that you dissociate with an 18 electron complex. Unfortunately, these early transition metals can't achieve 18 electrons from just adding alkyl groups. So we have some really quite exceptional examples here. This one I showed you how to make it, and this is going to be an 8 electron compound. What about the one on the left? The one on the left has a bis trimethylsilyl methyl ligand, and it has 1, 2, 3 of these bis trimethylsilyl methyl ligands. So how many electron species is the one on the left? On the face of it, it's a relatively easy electron counting problem. You have 4 electrons from titanium, you have 3 alkyl ligands, so this is a 7 electron species. So that species ought to be ringing every alarm bell in the book. It's got an odd number of electrons, it's got as few as 7 electrons, and yet I have to tell you this is a stable compound. It's very reactive, but thermally it's quite stable. And the reason it's so stable is because of the size of these alkyl ligands. What you have is a methyl group that has been modified by putting 2 trimethylsilyls on it. These trimethylsilyls are big, and they act just like our bulky phosphine ligands. They act as a sort of steric umbrella protecting the metal centre from any further interactions. And because we don't have here, we do not have a beta hydrogen. In the beta position there are silicon atoms here, or silicon carbon linkages here, so we do not have any beta hydrogens on these species, and so they do not undergo beta hydride elimination. They're sterically saturated even if they're nothing like being electronically saturated. What's transition metal alkyl chemistry good for? Well, this is really a slide that will touch upon and tease, if you like, for what will come in 3C32. 3C32 is called inorganic structure and function, where you will talk about not just how to make these compounds, but what to do with them. There's a lot you can do with a metal alkyl compound. Once you've got a metal alkyl compound, what you can do is react it with various electrophiles to synthesize functional groups on the surface of these species. But this is a reaction that I studied for my PhD. And what we do here is we take a metal alkyl and we expose it to alkene. We expose it to something like ethylene or propylene. What happens if you have the right metal alkyl is that you get coordination of the alkene, you get migratory insertion, as it's called, of the alkyl group. So this is carbon illustrates our alkyl group. And look where that carbon has ended up. The carbon has ended up 3 positions down the chain. What we've done is we've inserted an alkene into the metal carbon linkage. Now, what's that a recipe for? We've extended our chain by 2 units every time we expose it to a molecule of ethene or propene or butene or hexene. It's a recipe for polymerization. For all those who've done 2H11 should recognize this as being a metal catalyzed polymerization process to make a polyalkene. And these polyalkenes simply couldn't be any more important than they are at the moment. Polyethylene, polypropylene are ubiquitous materials for which, sort of modern life couldn't exist without. And these things are produced on the tens and hundreds of millions of tons every year. And it's all done through transition metal alkyls polymerized processes. Okay, so we've got various reactions with electrophiles here. Here we have some transition metal alkyl compounds. And transition metal alkyl compounds don't stretch our arithmetic abilities very much, since they are 1 electron donors, but it does give us an opportunity to exercise our electron counting muscles and wave our little pieces of paper in the air, wake up approximately 4:30 into the afternoon. So, what is the electron count for the compound in the top left of this slide? It is, so this species here, this is vanadium. Vanadium is in group 5. This is a cyclopentadienyl ligand, a 5-electron donor. This is a carbonyl ligand, a 2-electron donor. This is a phosphine ligand, a 2-electron donor. So 5 plus 5 plus 2 plus 2 plus 2 plus 2 is 18. So this is an 18-electron complex. What about the one here on the right-hand side? So what is the electron count for that compound there? I've tried to confuse matters by producing what is essentially a chiral compound by having 4 different alkyl groups on it. Yes, exactly. It is still, can't disguise that they are only alkyl groups, and that will be an 8-electron compound. What about the one in the middle here? Cobalt's in what group of the periodic table? 9. Cyclopentadienyl is 5. So 5 plus 4 plus 9 is 18. So that's an 18-electron compound. This cobaltocene here we'll talk about on Friday. That is going to be a how many? 19. Very good. Okay, so that's a 19-electron compound. And this one, a metal that we haven't encountered very much on this course, scandium. Scandium is in group 3 of the periodic table. So how many electron species is that one? I hear some 12, so let's see. 3 plus 5 is 8, plus 1 is 9. These are 2-electron donors, so that will be 11, 13. But don't forget the positive charge, so it's a 12-electron compound. Good, we all seem to be sailing through those. Now, at the end of the last lecture, we talked about alkene ligands. And so far this lecture, we've talked about alkyl ligands. What happens when you combine an alkene ligand and an alkyl ligand? Because in essence, that is what an allyl ligand is. We can think of an allyl ligand as the combination of an alkyl ligand and an alkene ligand. How do we make them? Well, we make them through taking, well, there are lots of different ways. You can use a metathesis-like route. What we're doing here is we're reacting a manganese pentacarbonyl anion, which is clearly a nucleophile, with an electrophilic organic reagent here, so an allyl chloride species. What happens then is you produce a metal alkyl, essentially. Only this is a special metal alkyl because what we have here is manganese pentacarbonyl. That is a 17 electron fragment. This is an alkyl group, so this is an 18 electron compound. But this 18 electron compound has a double bond pendant to it. And we know that a double bond is a potential 2-electron donor. In this compound, this potential 2-electron donor is not bonded to the transition metal, because if it were, then we would have an electron count of 20. And we don't want an electron count of 20. So it remains what I would call pendant or dangling. It is not interacting with the transition metal. However, if we heat this system up, what we get is elimination of carbon monoxide. So carbon monoxide is a volatile material. You heat it up and you're getting an entropic driving force for this reaction. You're generating free CO. And this alkene function can then come round, wrap round and bind to the transition metal center. So the alkene becomes a 2-electron donor for the transition metal center. But we don't draw it like that. We draw it as a delocalized system where all 3 of these carbon atoms are all interacting with our transition metal center. And if we do an electron count here, what's the electron count for this allyl manganese tetracarbonyl? Remember, if all 3 carbon atoms are interacting, it is a 3-electron donor. Yes, it's an 18-electron compound. So we've gone from an 18-electron compound to an 18-electron compound. Then we're kicking out CO, which would have given us a 16-electron compound. But of course, we've got this ready-made ligand just ready to come in and coordinate, and we go back to an 18-electron compound. But once you've coordinated this alkene, what we'll see in a slide or two's time is that you can draw 2 resonance forms for this species. You can draw a resonance form where one end is sigma bonded to the metal and the other one is a pi donor. Or you can draw an equally convincing species where it's the other end that is sigma donor and the other end is pi bonded to the species. And you know that wherever you can draw two equivalent resonance forms, then a better representation is as a delocalized system. And that's what we have here in our allyl ligand, a delocalized charge across these three carbon atoms. Here's another example of making these species. This is here palladium in oxidation state 2. If you add CO to this system, what you get is reduction of palladium. So you get reduction of palladium to palladium 0. Palladium 0 can do the process that we'll dwell on in more length at the final lecture of this course, oxidative addition. Oxidative addition across this carbon-chlorine bond here will give us an allyl ligand. And the allyl ligand is a 3-electron donor. We need to have a bridging chloride in order to achieve an electron count of what? So this is a square planar palladium 2. What electron count would you predict, and would you indeed find, for a square planar palladium 2 species? Yes. This is a 16 electron species. So remember in that first electron counting lecture, we said we essentially have what amounts to a 16 electron rule for these square planar organometallic species. So this is an example of a 16 electron species. Now, if you have a coordinated alkene, so if you start off with an alkene that's coordinated already. So here we have a palladium compound that has a coordinated alkene. If R was equal to hydrogen here, then this would be propene, but R might be something else. So we have a coordinated alkene molecule here. If you treat that with a base, if you treat it with something capable of deprotonating it, then that generates an allyl ligand. So one method is to take a coordinated alkene and to deprotonate it. Interestingly enough, if you take a diene, a coordinated diene species, and you protonate a coordinate, so if you deprotonate a coordinated alkene, you make an allyl. If you protonate a coordinated diene, you also make an allyl. So here we're using tetrafluoroboric acid in the presence of CO to protonate this coordinated butadiene ligand, and that gives us an allyl ligand. And this species here is cationic. So if you do an electron count of here, you'll recognise that you started off with an 18 electron compound and you make a new 18 electron compound here. And finally, the one that I guess all of you would have predicted, knowing what you know about the general synthetic methods for making alkyl compounds and their derivatives, that if you start off with a magnesium allyl compound. Now, I have to tell you that magnesium allyl compounds are not eta-3 bonded. Magnesium allyls are always eta-1 bonded species where the alkene ligand is pendant and not coordinated to the magnesium centre. Why is there this difference between the tendency of transition metals to form eta-3 allyls and magnesium and most other main group elements to form eta-1 allyls? Well, it brings us back to how alkenes and related species actually bond to the transition metal. So we did that a couple of hours ago. How do alkenes bond to transition metals? They bind side on, and you know what kind of bonding interactions? They do bind side on through what kind of bonding interactions? Yeah, so there is sigma donation of the pi electrons. So let's be specific about that. Sigma donation of the pi electrons. And main group elements might want to accept electrons. But what is it that transition metals can do that main group elements can't? Yes, this is the key point. Transition metals have occupied d orbitals that can do back donation of electron density. Main group elements don't. They don't have the orbitals that are occupied with correct symmetry to back donate into pi star orbitals. And so you won't often see coordination of alkenes to main group elements. And essentially what you're doing when you're eta-3 bonding an allyl group is you are coordinating the alkene part of that allyl group to your metal centre. And that requires the ability to both act as a donor and an acceptor. Okay, so we've got a bis allyl nickel compound, which I've asked you to count the electrons on before. This is going to be a 16 electron species. Right, so let's just reiterate the bonding modes of our allyl ligand. So allyl ligands can either be eta-1 bonded. If they are eta-1 bonded, then they are only sigma bonded. They are forming a normal covalent bond by sharing an electron with a carbon-based radical and the metal-based radical. So they are eta-1 bonded, in which case the alkene function is going to be pendant and not coordinated to the transition metal center. Or we can basically coordinate that alkene function to the transition metal center. So let's look at the different resonance forms if we do that. It becomes a 3-electron donor. So this is a 1-electron donor interaction. This is a 2-electron donor interaction. And you can draw one resonance form that looks like that. But if you look at these carbon atoms, how do these carbon atoms differ fundamentally from this end of the allyl ligand to this end of the allyl ligand? They don't. And so you can draw a perfectly reasonable equivalent resonance form that looks like this, where this end is a sigma bond and this end here is an interaction of the pi electrons with the metal center. If these two ends are equivalent, then a better way of representing this is as an eta-3 allyl species like that. Now this ability to form either eta-1 or eta-3 allyls is a little bit like the possibilities that we've seen in the past for halide ligands. Halide ligands can be either 1-electron donors or they can bridge, and they can be 3-electron donors. But of course that's between two different metal centers. We've encountered earlier today a nitrosyl ligand. Now a nitrosyl ligand can either be a 1-electron donor, in which case it's a bent ligand, or it can be a 3-electron donor, in which case it is a linear ligand. And an allyl situation is like that. So what we can have is either a 1-electron donor, or we can also coordinate the alkene function here and produce an eta-3 bonded species. Wherever you have this possibility of switching between eta-1 and eta-3 coordination, then you have the potential for ligand fluctionality. So even if you label both ends of your allyl ligand and you have a compound in which the species appears to be an eta-1 allyl ligand, then essentially this mechanism allows us to exchange both of those ends. And so what you find is that both ends appear to be bonded an equal amount of time to the transition metal because they're going through an eta-3 intermediate and they're coming off. We also have the potential for freeing up steric unsaturation. So if in that example I showed you on the previous slide, so if we take this example here, what we have here is a situation where what you start off with is an eta-1 bonded allyl ligand. And you may say to yourself, well, what I'd like to do is I'd like to exchange a carbon monoxide ligand for something else in a convenient fashion. Of course, having an allyl ligand gives you a built-in pathway for doing this, because what will happen is the CO ligand will be lost. That will form a very unstable 16-electron intermediate. The alkene bit of the allyl will come in and coordinate. That will give you an 18-electron species. But then, of course, it can come off again when another donor approaches. And so you can have a facile mechanism for exchanging carbon monoxide ligands with other species. OK, so here's our summary slide. I don't want to spend too long on it. What I do want you to take home from here is the key point here about metal alkyls not being thermodynamically unstable. These species are not thermodynamically unstable. It's just, or in an analogous fashion to we saw for group 13. The reason these transition metal alkyls are so reactive is because there's a low energy reaction pathway. And that low energy reaction pathway, in the case of these transition metal alkyls, tends to be thermal decomposition through beta-hydride elimination. And whenever you get beta-hydride elimination, you have a hydride cis to an alkyl. That reductively eliminates and gives you an equivalent of alkane. And that really tells you what is happening in these systems. And these transition metal alkyls, as with all good transition metal organometallic chemistry, are a route into all sorts of catalytic and stoichiometric reactivity.